In the previous video, we saw what we called an indicial equation, and that was r times the quantity of 2r plus 3 equals 0. We're going to focus on that equation and see how it can be generalized. For that, I want to go back even farther back to the first video where we saw a form of a differential equation that was x squared y double prime plus x p of x y prime plus q of x y equals 0. For this equation, x equals 0 is a regular singular point as long as p of x, lowercase p of x, and lowercase q of x are analytic at x equals 0. Focusing on that form, we can say here x equals 0 is a regular singular point of x squared y double prime plus x lowercase p of x y prime plus lowercase q of x y equals 0 if p and q are analytic at x equals 0. That is, if p of x can be represented as a power series centered at 0, so is equal to a naught plus a1x plus and so on, and q of x is equal to b naught plus b1x and so on. What we're going to do is we're going to take this equation that we're looking at and put sigma expressions in place of y double prime, y prime, and y. And then we're going to substitute in place of p of x, its power series, and in place of q of x, its power series. The result is going to look like the sum as n goes from 0 to infinity of n plus r times n plus r minus 1 c sub n x to the n plus r. That would be n plus r minus 2 for a second derivative, but we have a factor of x squared. Plus, likewise, x times y prime is going to give us the sum as n goes from 0 to infinity of n plus r c sub n x to the n plus r because of that factor of x. Lowercase p of x is a naught plus a1x plus, and I'll dot that there. Moving on to the q of x y term, y is the sum as n goes from 0 to infinity of c sub n x to the n plus r, and q of x has this power series representation, which I'll write as b sub 0 plus b1x plus dot, and this equation equals 0. One of the virtues of what I called in the first video in this set of videos was this Cauchy-Euler-esque form of x squared y double prime, an x with a y prime term, and then a y term, is that in all of the sigma expressions that we have here, we have c sub n x to the n plus r. That makes it easy to write down the term that has the smallest power on x. Why that term? As we said before, that term always exists, and I'm going to say this is what Frobenius gave us. The smallest power on x, since n is equal to 0 and x to the n plus r is in every term, is x to the r. For the first sigma expression, we get that when n equals 0, and so we have r times r minus 1 times c sub 0, I'll say x to the r there. The only way to get x to the r from the second term with that power series representation for lowercase p of x is to use only the a sub 0 term. If I multiply by a1x, then I don't have x to the n plus r. So maybe a mental exercise is that we're taking this sigma expression, distributing it into the parentheses in front of it, and we end up only with a sub 0 times r c sub 0 x to the r. Likewise, in that third term, if we were to take that sigma with x to the n plus r and distribute it, the only term that we want is the one that has the b sub 0. So that's going to give us b sub 0 c sub 0 x to the r equals 0. Now remember, we want solutions that are good for a whole interval, not just one value. So we're not considering just x equals 0. This equation needs to hold true for multiple values of x. So we can disregard the x to the r. Likewise, we said we aren't going to let c naught equal 0. We lose everything if we do that. So c naught is not going to be 0. That makes r times r minus 1 plus a sub 0 r plus b sub 0 equal to 0. That is the general indicial equation. It's worth noting that our indicial equation is r times the quantity of r minus 1 plus a naught r plus b naught equals 0, where a naught is the constant of lowercase p of x and b naught is the constant of lowercase q of x. Let's put this into the context of the previous exercise. We had 2xy double prime plus 5y prime plus xy is equal to 0. And remember, we were looking for this like Cauchy-Euler-esque form. In particular, the first term should be x squared y double prime. In order to make that happen, we're going to multiply this equation by x and divide it by 2. So we have x squared y double prime plus 5 over 2xy prime plus 1/2 x squared y is equal to 0. Now something that's a little bit tricky to remember is, so this first term is, x squared y double prime. The second term is x times lowercase p of x y prime. And that third term is q of x y. That third term's not the tricky part. The tricky part is that this x is not part of lowercase p of x. So here we've got that lowercase p of x is equal to 5/2. Lowercase q of x is equal to 1/2 x squared. We said that a sub 0 is the constant term of p of x and b sub 0 is a constant term of q of x. That makes a sub 0 equal to 5/2 and b sub 0 equal to 0 because q of x has no constant term. Now for that indicial equation, r minus 1 plus a naught r plus b naught equals 0. So we have r times r minus 1 plus 5/2 r from a naught plus 0 from b naught equals 0. Clearing the fraction gives us 2r times r minus 1 plus 5 is equal to 0, which gives us 2r squared minus 2r plus 5r is equal to 0, so that 2r squared plus 3r is equal to 0, giving us r times 2r plus 3 equals 0. That's exactly what we came up with when we did this in the previous example. So based on this, we would then say that r is equal to 0 or negative 3/2. And I'd say in your work, if you're asked for the indicial roots, this is a way to get them. And then that's actually going to determine what kinds of solutions we might expect, depending on whether they differ by an integer or not. We'll get to that later. But then as you're doing your work and you come up with this organically later, it serves as a good check that you have the correct indicial roots.